All right, thanks, Brian. Yeah, so as Brian mentioned, I'm not new to the lab, but I'm new to the position of instrument scientist. So if I make any mistakes, I'll use that as my excuse that I'm the new guy. I'll start off by acknowledging the team. It's a great privilege to work with this team. I won't go through everyone. I'll mention Hasina started the imaging effort here, starting with just sort of a test beam line, and it was done on a sort of a proof of concept basis at first. It became popular, and finally we took this beam line and dedicated it to neutron imaging. And it's been fully in the user program now for quite a while. The instrument at the HIFER is what I'm talking about. So we have one dedicated imaging beam line here at Oak Ridge right now for neutrons, and that's at the HIFER. But we also do some imaging at the SNS with, on other instruments that aren't dedicated to imaging, but we can still do imaging here at the SNS as well. So the goals of the talk, I'll break them down into three categories. We want to see what we can do with neutron imaging, compare it to other techniques, and when do we choose it? You've probably heard several times, you always need to ask yourself the question, why neutrons? And you're not going to use neutrons if you could do it by other means generally, because neutron sources are few and far between. So we want to know when we're going to choose neutron imaging, understand the basic instrument layout and the principles of how it works, and then learn by example. I just want to give some examples that hopefully will illustrate all of this pretty well. So imaging is important in science, and you can see that by taking a look at Nobel Prizes that are related to imaging. And so I'll mention X-rays. The Nobel Prize for X-rays was given in the early 20th century. And right from the start, the value of X-rays for use as an imaging probe was recognized. That was recognized in the Nobel Prize, and everybody knows about medical X-rays, and that's kind of the example I'll give. If I'm talking to a non-scientist trying to explain to them what I do here at the lab, I'll say, well, you're familiar with the medical X-ray. We do the same kind of thing with neutrons. So that goes way back to the 1901. Radiography is great. A medical X-ray is a two-dimensional radiograph. There was a Nobel Prize awarded in 1979 for tomography, and that's important for imaging. And that's where you basically, a radiograph just gives you the average transmission all the way through some sample. But if you're looking at some complex structures, you need a three-dimensional rendering of what's going on inside. So that technique is called tomography, where you can take a series of radiographs and you do some mathematical manipulation, and you can reconstruct the entire volume. So that earned a Nobel Prize in '79. And of course, you could image using lots of different probes. So the list here goes on with electrons. If you want to image atomic level structures, then you need to do something like electron microscopy. MRI, of course, is another technique that was recognized in medicine. And finally, even the CCD detector, charge coupled device, that's on the Nobel list because it just goes to show imaging is so important in science and medicine, and these devices that allow us to get away from film to have electronic images play a crucial role. Hey, what about neutron imaging though? You notice there was no neutron imaging Nobel Prize on the list, so I'll leave that as an opportunity for you guys. And so even though neutron imaging has been around for a long time, it was back in the 1930s, it was demonstrated, and then you have places like this that give you capabilities where you can do some scientific work with neutron imaging. And so here's a schematic of what it's all about. So we're basically measuring the shadow of an object using neutrons. So it's a transmission image, and one shadow we'd call it a radiograph, and if you have a series of them, you could construct a tomograph, which would be the 3D equivalent. And so these images are collected at different angles and reconstructed in 3D. And so the basic scheme here is we have some neutron source, and we have to pass the neutrons through a small aperture and basically make a pinhole camera. And you know, we have an eclipse coming up next week, so a lot of people are going to do the pinhole camera thing where you pass the light through a small hole and you project the image. You don't need any focusing, when you do it that way, because of basically the relevant parameters for your image resolution is the size of the aperture in relation to the path length of the neutrons in this case. And so what we would do is we have some incident neutrons. Here, they go through an object and hit a detector, and ultimately we get an image. And here I'll try to show you a video. And this is a link to a YouTube video that it shows a nice example of what we can do after you've done a reconstruction. So the image here you see, that's a turbine blade for an aircraft engine. And it's full of detail inside. So let's take a look at the video. This is a YouTube, and it doesn't have any sound, so we can just watch and maybe I think it's self-explanatory. I guess I need this one. There we go, full screen. So that just shows. This shows you all these radiographs, kind of what that looks like as you spin it around, but you can now zoom in, and this was constructed by Jean Ballou, who's one of our team members. He's a computer expert and a physicist, and this is really great. So he does a fly-through of this turbine blade. And it's colorized according to how much the actual blade deviates from the engineering model. And so this is one of the uses of neutron imaging is, you could use it as an inspection tool. Kind of the simplest approach is you have an image and you see, where do you have voids, where do you have cracks, and where does it deviate from your model. So that's up on our website. Okay, how do I get out of this thing? Escape. Okay, thank you. Okay, and we're back to the presentation. There we go. Okay, so it's we want to go beyond just getting images, though, and getting pretty pictures, you might say. And so quantitative neutron imaging, the key factors here, the transmission, just the ratio of the transmitted to the incident beam is going to follow an exponential law. But if you break that down further, this attenuation coefficient depends on some inherent properties of the elements that comprise your sample. And so this cross section, it's going to be wavelength dependent for one thing, and of course it's going to depend on what elements you have present. And the other part that's relevant to the sample is the density of the nuclei. You've all heard already, I'm sure, the neutrons are interacting with the nuclei in the sample. So part of the challenge, when your attenuation is kind of wrapped up in both the cross sections of the atoms that are in your sample and the density of those atoms. So sometimes that's a challenge to kind of unravel those two effects. Now, whenever we do an experiment, I should say before you do the experiment, we want to have some idea of what we expect to see as far as transmission. And you could easily make at least an estimate by just doing some calculations. You could look up cross sections in the literature, but now it's even easier. There are some nice online transmission calculators. And so, for example, suppose I told you that I want to study a rose that's within a lead cask, because it's such an important physics problem, right? So if I told you that, you might may think I'm crazy for many reasons, but for one thing, your intuition tells you there's no way you're going to see a rose inside of a lead cask, right? And at that point, that's where it's important to calculate these things ahead of time, because you got to convince yourself and you got to convince others that, yeah, this might work. I might actually see something with this technique. And this is generally true no matter what technique you're going to use. Before you actually do the experiment, you want to have some idea. So in this case, transmission, let's say, for example, through 2 centimeters of lead. Suppose my container has walls 1 centimeter thickness. I've got to go through both sides. Well, it turns out for neutrons, and I've calculated it here for 2.6 angstrom neutrons, if that's what you'd consider a cold neutron. That's the peak of our wavelength distribution at the CG1D Neutron Imaging Instrument. 2 centimeters of lead, not bad. We get 42% transmission through that. So that's telling me it might be feasible. But then you say, well, if you go through all that lead so easily, how are you going to see the rose? Is it going to do anything to the beam? And I don't know the chemical composition of a rose, but the relevant thing for neutrons is probably the water inside. And water, hydrogen in particular, is highly attenuating. So for example, if I went through the equivalent path length of water, the neutrons, you're not going to get anything through. But maybe more relevant, let's say I'm looking at a rose and I might have the equivalent of a couple millimeters of path length through water. And now I'm talking about a transmission that's feasible. I might actually see something. And sure enough, you can do this. Now, this was done, I didn't do this. Dr. Lehman beat me to it, but that's an actual radiograph. There's a rose in a thick-walled lead container. And that's a nice illustration, I think. I could show you the table of cross-sections of the elements, but this kind of wraps it up. And it's one of the reasons why you might choose neutrons instead of X-rays, right? Because X-rays are abundant, they're powerful sources, but if you need to find hydrogen among other elements, neutrons are great. Other distinctive features, really in comparison to the other instruments, you've seen that most of the instruments here, what we're looking at are the scattered neutrons. And we do that, because with diffraction, for example, we can determine crystal structures. And so we're now investigating length scales on the order of angstrom here with diffraction. And for non-crystalline materials, we see structures on a variety of length scales. And that's why we have a suite of instruments here. We can look at different length scales. You can look at diffraction. You can look at inelastic scattering. We're kind of the oddball here. We look at real space images. So that's one thing. It's not reciprocal space. It's real space imaging. And in principle, pretty easy. In practice, not so easy. And here are just a few examples, where you are, let's say, investigating the root system of plants. And the other thing I want to emphasize, though, one of the big limitations with neutrons, and this is worldwide, and there is a big quest within neutron imaging to improve spatial resolution, but 100 microns is routinely achievable here and elsewhere. If you really need 20 microns, yeah, we can do it. There's a trade-off. You typically have to count longer. We have to use different kinds of detectors. Everybody's shooting to get down to the micron scale with neutrons, and hopefully, we're in that race too, and hopefully we can do that in the coming years, let's say. The other things to consider, neutron transmission depends upon the sample composition thickness and neutron wavelength as well. So here's just transmission versus wavelength. Shows you that basically the long wavelengths or the slower neutrons are more attenuated. The transmission is less. And you can think of it, the simple way to think of it, if the neutron's going by the nuclei fast, there's a less chance it's going to get captured. And this is good and bad. So we operate here at 2.6. It's nice because you can see a nice contrast between different elements. Let's say aluminum is quite transparent. There's a lot of transmission compared to, say, copper and zinc. And these examples also let you know, if you look at the length scale examples here, we're talking centimeters. So we can take a look at big objects with neutron imaging. Now, time of flight imaging, which we do here at the pulse source, we can discriminate the different wavelengths by the time of arrival at the detector. So instead of one image that's averaged over all the wavelengths, we can slice it up and look at the wavelength dependent. And so one thing you can just see from this graph, you may have different contrast in different regions, or you may be able to just to pick out wavelengths where you'll get the appropriate transmission. But even more important, I think, when it comes to wavelength resolved imaging, is you can make use of the fact that your attenuation or your transmission, however you want to look at it, depends upon both the absorption within the sample and scattering. So imaging and diffraction are not entirely unrelated. There are diffraction effects that are wrapped up, or in general scattering effects that information is there somehow. So whereas other instruments, they're collecting all these scattered neutrons, well, we're detecting their absence. And with the so-called the Bragg edge technique, that's where you can, if you were to plot out transmission versus wavelength for a crystalline material, you may see some sharp features. And these are called Bragg edges, and that's where basically where Bragg's law can only be satisfied up to a certain wavelength. Sine theta can't be bigger than 1, so the transmission will have a sharp change when you no longer can detect that neutron wavelength. And you can do a lot of stuff with that. I won't say much about that because that's an entire talk right there. So let's move on. The goals were, number one, to see what we can do. Hopefully I've given you a little flavor of that. But let's move on to understand the basic instrument layout and the principles of acquisition and analysis. So here's a photo of our beamline at the HIFER. A few of you have been there. It's been great. This picture was taken standing up on a mezzanine, and so the neutrons are coming in this direction. We have this big tube. The purpose of that tube is just so the neutrons can travel this large distance. It's about 6 meters, and we don't want the neutrons getting scattered by air, causing background and losing intensity. So that's a helium-filled tube that allows neutrons to go from the aperture, would be back here. It'll travel through this tube. We've got some slits on the end of the tube. We can control the beam size to make it appropriate for the sample, which is going to be right in front of the detector here. And we have detectors in this position. We alternate between detectors there too, depending on what's appropriate. You can see some people back here, so this gives you a bit of the scale of the instrument. Our instrument, the boundary of the instrument's an open fence. It's much different than some of the instruments here at the SNS. They're within a cave. The intensity, the radiation is so severe. Sometimes you need a wall. Here, we just have a fence boundary, and it's kind of nice. We can see through it. That's helpful sometimes. We are actually, though, going to put a solid steel wall on the back end of this to cut down radiation and background. So that's the left panel. Over on the right, this shows you, it's a photograph of our main workhorse detector, and I've overlaid some notes. So the neutrons are incident on this scintillator screen, which it's an aluminum plate, and the backside of that plate is coated with a scintillating material that contains lithium-6. And what happens, so that scintillator is within this light-tight box. Neutrons hit it, visible light is emitted. So now I've got a visible image of my sample on that screen, and that image, we're going to bounce it off of a mirror and then go to an optical camera. And the mirror just gets the camera out of the direct beam, because a lot of the neutrons are going to pass right through everything and go over here to the beam stop. And here's the sample area in particular. So this would be a large sample, obviously. For tomography, we put a sample on a rotation stage, and we take hundreds of radiographs at slightly different angles. You have to go at least 180 degrees to get a tomograph, or you can go 360. Enough said about that. So that gives you a sense of the scale. So detection of neutrons, and I already mentioned this, so light is emitted after capturing the neutrons. This gives us a good signal-to-noise ratio. So we have a grayscale range that really allows us to discriminate between slightly different transmissions, and so that's one of the big advantages. Other thing is a large field of view. Our beam cross-section is as large as about 8 centimeter by 8 centimeters, and scintillator screens of that size are readily available. They're not outrageously expensive compared to other types of detectors. So that's the big advantage. A big disadvantage is the spatial resolution is limited. And in part, that's the scintillator itself in part, because as the neutrons are captured, light is emitted within this scintillator. It's basically a paste. It's painted on there. So each spot of, from each neutron capture is going to produce sort of a sphere of light there. So that's going to limit our resolution spatially. And well, the other limitation is time resolution too. You can't. So if I wanted to acquire images rapidly, this is not the best choice. The quickest that we ever acquire using our scintillator with a CCD camera is about 1 radiograph per second. So there are cases where if we want to do a dynamic study, we want to capture several frames per second, we'll go to a different type of detector, which is this one. So microchannel plate detector, it's a more direct type of detection. So this is basically a piece of glass with holes in it. The glass is doped with a material that will basically eject eject electrons after the neutron is captured. The electrons go into these channels, and there's a strong field there. Basically, you count electrons ultimately. So you've got a chip, an electronic chip that gets an image based on the electrons that are ejected. And this one can acquire images very rapidly. So we've got the events are encoded at an XY position and time of arrival to high precision. It has a high efficiency, very little readout noise, and it's not too bad. The other challenge with neutron detection, you want to detect just the neutrons, and there's also a lot of gamma radiation. Whenever you're doing a neutron study, the sample might be emitting gamma radiation as it absorbs some neutrons. So your detector, sometimes that screws up or produces noise in your detector. But this one's it's feasible to use for neutrons because it's not that gamma sensitive, and becoming commercially available. But the limited field of view, that's just a cost issue for one thing. It's quite expensive. That detector, so our scintillator is on the order of 8 centimeters square. Our MCP detector is 2 centimeters square. The beam at CG1D, it's polychromatic, and it peaks at about 2.6. And you've probably heard a lot about the thermal versus cold neutrons. So this is in the region that we would consider cold neutrons, and that's because these neutrons have gone through a liquid hydrogen moderator. They've come to thermal equilibrium with something that's cold, and that gives them longer wavelengths. For us, I mean, as I mentioned earlier, the wavelength, the precise wavelength isn't that important. What's important for this instrument is sort of the range of wavelengths that we have. So, okay, data normalization for imaging. What we have, if you look at a raw image here, here's the image with the sample in the beam. Here's just an open beam, no sample. Look at that, you get like this plaid shirt pattern, and that's because our neutrons have traveled down a guide. This is just polished surfaces. So the neutrons bounce around in that guide, and they get this structure. The intensity varies quite a bit spatially. That's not a killer though for us, because what you do for a normalized image is you take the raw image and you subtract away the dark field is just your electronic background. So image minus dark field, divide it by the open beam minus the dark field, and then you get a normalized image, which in this particular image, there's a clamp here that's holding an aluminum vessel that has a rock core. In this very dark region here, this experiment was to look at water propagation through a porous rock core. So there's the water coming up, and it appears black because it's so attenuating. Yes, sir?
So it might just be an illusion because of the background in the image, but it seems like there's some, you can actually tell that there's a cylindrical shape to the object.
Mm-hmm.
That seems to be missing in the normalized image. I'm wondering if that's an illusion to get rid of, or if some information was lost.
Well, no, the normalization shouldn't cause any loss of anything important. So I don't know. I'm not seeing that. So you think in the raw image?
Yeah, I think in the raw image, it's probably just because the background is giving it like this shading.
Yeah.
Okay.
Yeah, that's probably it. Right. You get the 3D illusion if it's shaded like that. Yes.
Kind of follow up. How often do you do a normalization procedure? So do you obtain the open beam dark field?
So we collect usually once a day. We'll collect an open beam image because the flux at the reactor it changes slightly and continuously throughout the cycle. So actually. We just want to keep those updated, but they're basically the same. I could collect an open beam at the beginning of the cycle and use it throughout. But as far as how often we do, I mean, really, you wouldn't want to present an image like that usually. You always want a normalized image. So the typical experiment, maybe at some point each day you collect some open beams and then you collect all these raw images. And the process of doing this is automated through the analysis software. And I think the next slide, did I mention? Well, it's coming up. So certainly every, sometimes you're just collecting a series of radiographs. That's what we've been doing for what we're running right now. We've got a furnace our samples in the furnace, and things are changing as we heat it. So we have a series of radiographs, but we could automate that normalization. For tomography, you not only normalize each radiograph, but you have to do the manipulation to actually convert to a stack of images. So let's see if I can go through this. So you can tell these are raw images. You can see the beam structure there, that this is a root system, plants growing in some little aluminum container. So you got the raw images, and then you normalize. Now I've got a stack of nice normalized images here, each image at a different angle. The transmission, so it's a transmission map, but it's the transmission all the way through that cylinder. And then the process, you can think of this as if you take a slice in the horizontal plane for each one of these images, you can construct a new image that projects that slice for different angles. That's why it has that appearance of it swirling around. So each horizontal slice has gone through 360 or 180 degrees. Ultimately, and these are quite dark, you're going to get another stack of images that the distinction for these, not only are these images showing you slices in the horizontal plane, but each pixel is just that element, that volume element. You don't have to worry about the path length through the sample. We've taken care of that in this process of normalization. And then ultimately what we look at is something like this. This is a kind of a picture you'd show in a journal. Yeah, we did tomography, and that's the result. And you really, even as a user, you don't need to worry about all this process. What we're doing lately, which I really like, the data analysis guys are giving us some web-based tools. You may have already been on the analysis sns.gov website. There are lots of great tools there. And so, like as I go through this with the students, if we get to it, I guess a few of you are here. I don't know, we haven't even gotten to this. We spent so much time at the instrument the other day, but we have these Python-based tools now, and we do this with Jupyter Notebooks. Some of you you know about that. Where basically, if I want to do that tomography reconstruction, I can just open my web browser to this Python notebook, and I put in the sample-specific information, and it does all that manipulation. That's a huge improvement for what we've used in the past. We have some expensive, commercially available software that I hate now compared to this. It's so much easier. So, real nice. For both tomography or even what the data analysis guys will do, as needed for users is make custom notebooks. So you might be doing something very particular where you need to normalize your images in different ways. Because, for example, it's common that you don't want to normalize just to an open beam. You may want to normalize to some initial condition and see how things change. You may want to filter out certain features. So they could make a custom notebook that does those sorts of things. So we've talked a lot about the conventional techniques that I would say are routinely available. Transmission radiographs and transmission tomographs. There are other things we do, and I'm not going to dwell here, but we'll go through them on examples. What you might call stroboscopic imaging is if we have some cyclic process, and we've done this with fuel injectors, for example, where we fire a fuel injector over and over, and the neutron flux isn't big enough that we can just capture one radiograph and see what's going on at any given point in that firing cycle. But we fire it over and over and synchronize it with the MCP detector, and we can say something about what's going on. So we do some of that, stroboscopic imaging, or even processes that happen fast. And that's actually becoming a bit common now. So we use the MCP detector for like water uptake that might advance quite quickly. Polarized neutron imaging. This is something really new for us. We've done it. We devoted a cycle to this recently. We'll probably do this once a year, is devote a cycle to polarized beam imaging. So the neutrons, the raw beam that comes out of the guide is randomly polarized. And you've heard, I think there were some talks about polarized imaging. So I'll try to put it in a nutshell. I mean, what you can do is you put a spin filter in the incident beam, so you get just one polarization incident on the sample, and then the sample, the magnetic moment of the neutron may interact with the sample and get flipped, and then you've got an analyzer after the sample, so you can detect the effects of the magnetic field. You could even image the magnetic field itself, even that surrounds the sample, with this technique. And so we're doing some of that now. We devote a cycle to it, and partly because it's just so technically difficult. We have to set up a lot of equipment, and it takes a long time, so we might as well just do it all at once. And then there's these energy selective techniques that, this was newly implemented at CG1D, actually. So I mentioned that at the SNS, we can do energy selective techniques by virtue of the pulse source, but we could also monochromate our beam at the HIFER and take a given slice out of that spectrum if we wanted to. And this goes hand in hand with polarized beam. Actually, our last run, we ran the polarized imaging with a monochromatic beam in order to get some quantitative information out, because you can't sort things out with the polychromatic beam very well. And then phase contrast imaging is under development. So lots going on here. Okay, so the final part, examples. We do have a wide range of science that goes on. That's one of the nice things about working on this beamline. And then additive manufacturing, energy storage, plant systems, you name it. So I'll try to give, hopefully I'll got a good flavor. We already looked at the turbine blade. I'll skip over that. What we're doing right now, actually, during the neutron school, is a high temperature experiment. So sample environment, this is something that I enjoy. My introduction into the neutron world was as a sample environment guy. So I like doing experiments with furnaces and cryostats and all this sort of thing. In the early days of our imaging instrument, we hardly ever did special environments. We did a lot of room temperature stuff. But increasingly, we're looking at things at different temperatures and pressures, different conditions. So this experiment, we have this vacuum furnace here that can go, it can go up to 1500 Celsius, even higher. But for this experiment, we're going up to 1500 Celsius. We're taking these little alloy pellets. So these are metal alloys, cobalt, copper, chrome, and some other. So we have some binary, we have some ternary alloys, and the scientific problem is melt separation in the melt. So some materials, when you melt them, you have phase separation even in the liquid, and that has consequences, of course, for you know, what happens when you cast a material, and you know, what does the solid phase look like. So we are actually imaging, we're heating these materials up. This shows us loading into a ceramic cell. A little pellet goes in the cell, we load it up. That's a raw radiograph. So there it is inside this furnace. It's hanging in there, waiting to be heated. I didn't have time to add a lot of stuff, but we actually, we were seeing in real time. This is one of the reasons why we stayed at the instrument so long, because it's fun. I mean, you're out here and we start to heat it up, and you can tell this is before it's melted. The pellet doesn't have exactly the shape of that container, but over time, when we were looking at these slices last night, I mean, you can see that ball just kind of collapse and take the shape of the container. And we were also imaging. It should be in this image. It's just not showing here in this projection. It's phase separated. It was phase separated, you know, as cast, and we heat it up, we melt it, and we can see the phase separation, and we can see the different regions, you know, moving around as we heat it. So that's going pretty well, especially technically. That was a, you know, a first for us going to that temperature. So there was a technical challenge there, and that's good. Another thing that we get a lot of is, you know, the biology-focused experiments. In this, we've had a student here who from Princeton who's had an extended stay here, and this is his work. You know, he has these plants that he fills this plate style holder with soil, and what he's interested in is really the roots here. And this shows the plant when it's nice and looking good and it's been watered. But what he's really interested in is what happens as I stress that out and I don't water it, and he's, you know, looking at how root systems adapt to drought conditions, and the ultimate goal is how do we have drought resistant crops and that sort of thing. Here's an example from the geosciences. There's a lot of interest in how fluids propagate in porous media. How does water, or how do pollutants propagate within soil and rock? And there are techniques like fracking that people are trying to use to extract oil, and lots of questions. Is this safe or not for the environment? So people study these sorts of things, and here's an image of a rock core that they've intentionally cracked, and they're studying the details of how water propagates within a crack, through pores. This was done with the MCP detector because we were acquiring it rapidly. Biological examples. So we don't hurt any animals. I wanted to make sure anyone thought of that. But there's a lot of biological studies have been done, especially in the early days. And this is where Hasina really started this instrument and formed some collaborations that were, a lot of them were biology focused. So there are postmortem studies of tissues, and here's from a tomographic reconstruction. You can see the damaged tissue here. Basically, so one of the things about this that's significant is it's a non-destructive alternative to the way a lot of biologists will take tissue and slice it and stain it. You can do this sort of thing in a neutron beam non-destructively. Similar studies, you know, showing optical photographs and how with neutrons, because they're so sensitive to water, you see differences in the transmission, and that is, again, it's non-destructive, and you may see features you don't otherwise. Forensic science. So Hasina, again, she has some stories to tell. You may have heard there's a body farm at the university, or associated with the University of Tennessee, and this is where, you know how when you watch these crime shows and the coroner can come and say, yeah, this guy's been dead for 10 hours or 2 days or whatever. So they study how tissues decay. Not a very pleasant topic, but she actually looked into, I'll advance the slide, so, you know, are neutrons useful in this regard? And, you know, so she's looking at how tissue, the transmission changes from day to day. I guess, you know, not that sensitive in this example, but, you know, exploring ways maybe we could use neutrons to help the forensic scientist learn more about how tissues decay. Time resolved studies. So here's an example. transportation research, the fuel injector example, I mentioned this, so what they did, we don't actually have an engine running for this experiment, but what we had was, we simulated the injector firing, and they've got a big rig. There's some high pressure hoses hooked up here. A fuel injector is hanging inside this chamber, and they put optical windows on it. For the neutrons, it's just an aluminum window. And this was one of these stroboscopic studies where they are firing the injector, and it's synchronized with the MCP detector. And this is a good example. This study, this team, they did X-rays and neutrons. And with the X-rays, they studied the details of the fuel spray. With X-rays, you can acquire very rapidly, and you can see the spray. The X-rays aren't that good for penetrating inside the injector and telling you what's going on inside the injector. So that was a neutron part. So we're firing that injector, and over time, by synchronizing several pulses, we could detect things like is cavitation occurring within the injector, for example. And since fuel injectors are such a mature technology, they're trying to optimize every last fraction of a % of efficiency in these. So they want to know the details of what's going on inside the injector. Tomography of a exhaust gas recirculator. So more transportation research, and a lot, even the same group has studied, what's happening non-destructively inside these filters. How's the soot building up, and how can we improve these types of devices? Here's an example that makes use of this Bragg edge technique, and this is one where, let's see, where do I start? Well, let's start here. There's an optical photograph. It's just a hunk of metal. So this is an Inconel metal that was deposited. It was formed through 3D printing, additive manufacturing. And it's composition-wise, it's a uniform piece. It's really boring. It's just a hunk of metal. So what's this DOE here? How do you see that? Well, what they've done, when they built this up, they were able to control grain orientation to some extent, so that you had some regions of this were textured, and in other regions the crystallites were randomly oriented. And that shows up with time-resolved neutron imaging because of the scattering effect. And if you have your crystal grains are aligned, then the Bragg features are going to be enhanced there. Therefore, the transmission is different, and that's ultimately all we see with a neutron imaging instrument experiment is transmission. So we have to relate the transmission back to what's, it's either composition, density. In this case, it's crystal orientation. So that's kind of the next level. It gets quite complex to analyze this data. We have a postdoc, Dian Song, who is working out a lot of the analysis for this type of data. And this plot here, transmission versus wavelength, you can see these sharp features. These would be this is what you call the Bragg edges. And each one is associated with a diffraction peak, 400 there, 311. So you go through it, and this is where it's related to diffraction. And there's just a blow up of that. Highly textured polycrystal there. The researchers cleverly printed out the letters DOE so they could get some brownie points with the Department of Energy. And I wonder if the movie would work. So my own research, I look at high-entropy alloys, and I'm starting to see if maybe this is Bragg edge technique. Is it useful for high-entropy alloys? I had some samples that went through a fatigue study. Obviously, there's one that went to failure. And even the surfaces are faceted too, so it's quite interesting. And I believe they're faceted because there are very large crystal grains within the sample. And sure, Bragg edge imaging is showing that the contrast variation here is due to the Bragg edge effect. Let me see, does this play? I think I had a movie here that, yeah. So what appears to be moving there? Nothing is changing in the sample. What's changing that makes it appear to, what makes it a movie is that we're sweeping through a range of wavelengths. And so as any particular grain satisfies the Bragg condition, it gets darker. And so what I hope to do ultimately with this, we could analyze, maybe, do we have preferred orientation in different areas? Can we say something about the grain structure? That's ultimately one of the things I'm interested in doing. This was just sort of a proof of principle experiment. All right, I think that I'm about okay on time, right? We'll have some time for questions. So I'll just summarize here. So neutron imaging, it's growing here as far as, we're expanding the capabilities of our instrument at the HIFER. So we're out in the Cold Guide Hall, Cold Guide 1 at the HIFER, and lots of activity there. What about the SNS? We someday maybe we'll have a dedicated imaging beamline here, but we don't have to wait for that. We're doing studies already, the Bragg Edge studies. In fact, next week we'll have a run on the SNAP beamline, and we've got a few things lined up there. So this is real exciting, especially for a lot of us in material science, because those crystallographic effects are of interest. Diverse applications. So we analyze what categories of experiments we're doing, and so based on publications, you can see we do quite a variety. I showed you some examples like from geoscience. Culture, that would be like archaeological artifacts. We've looked at that, and that's where the non-destructive part is really valuable, right? If there's some artifact, you don't want to have to slice it open to determine how they made it, how they cast it, and so a significant fraction of the experiments fall in that category. Materials, that's where I like to work. Industry, so we've got the automotive applications and that sort of thing. Life sciences, energy applications. In the large fraction, even worldwide, goes into development of the instrument itself. So we cover we cover a lot of different science areas. Again, for neutrons, you always have to ask yourself, why neutrons? Do I really need to use neutrons to solve my problem? But if so, this is a tool that's here for a wide variety of scientists. Now, to summarize, the neutrons are ideal for certain imaging applications, especially the sensitivity to hydrogen comes in really handy. Sensitivity to lithium is another one. I guess I didn't show any examples, but with all the research and lithium batteries, we've had some experiments, where people map out the distribution of lithium and then the migration of lithium in an operating battery, for example. So there's another example of where the neutron contrast difference, compared to other techniques, is the reason you choose neutrons to study things like lithium batteries. Isotope sensitivity is another one. And the penetration into large samples and sample environments is a key factor too. Spatially, we are quite limited, 80 microns for routine work, 20 microns we can do for radiographs that would require maybe a half hour to acquire. And the capabilities are steadily improving though. So hopefully you'll see things get a lot better. And so again, there's the team, and thanks for your attention. Yeah, thank you. Maybe I'll do that. I have to run back to the beamline first. So I've got my, HIFER's running this experiment. So it's the neutron school experiment. It's also involves an outside user. So there's a student from UC Riverside working hard right now at the beamline. So I'll go back and help them. Okay, thanks.